Okay, so here is a little lecture on looking at equations and determining the domain of the equations. So the first class of problems are polynomials. And polynomials are functions as such. So it could be a constant, that would be a horizontal line. We could have a linear function, 3x minus 2. We could have a quadratic function, 5x squared minus 10x plus 7. You can keep adding on higher order terms by adding x cubed, x to the fourth. So now the domain for polynomials is all real numbers. So we say in interval notations from negative infinity to positive infinity, but not including that. So that's using interval notation. So that's kind of the simplest situation. The next one are rational functions. So the rational functions are the ratio of polynomials. So the simplest rational function would be 1 over, say, not the simplest, but a simple kind of situation would be 1 over x minus 3, or any constant over some value x plus or minus something. And these are good for all real numbers except the values of x, which cause the denominator to go to 0. So in the simplest case, we can just set it equal to 0. X minus 3 equals 0. Solve for x, so you get x equals 3. So this is the x value is not in the domain, but all other values are in the domain. So the way we do that is we would start at negative infinity, go all the way to x equals 3, but not include 3, and union that with 3 to positive infinity. So if you just have a single term in the denominator, you figure out what value of x, that goes to 0, and then just do that. So if this was x plus 2, if I had 1 over, or 4 over x plus 2 is my function, then I would say, okay, what value of x makes x plus 2 equals 0? So you get x equals negative 2. So the domain would be negative infinity to negative 2 union with negative 2 to positive infinity. Now if you have a rational function that has a quadratic, if you can factor the quadratic, and it really doesn't matter what I have in the numerator, because that doesn't affect the domain. So it can be any polynomial. So I'm just going to make one up here. So what you do is you say, okay, what values of x cause x plus 3x plus 2 equals 0. So when you have a quadratic, you factor it. So I get x plus 2 times x plus 1 would be the correct factorization. And I want the values of x which cause this to go to 0. So there are two values of x, one where x plus 2 equals 0 and x plus 1 equals 0. So we take this factor, set it equals 0, and solve for x. So we get x is equal to negative 2, which is the solution, x equals negative 1, which is the solution. So we would order these in from most negative to most positive, and we have to have 3 parts. So you'd say negative infinity to negative 2 union with negative 2 to negative 1 union with negative 1 to positive infinity. Notice these are curved brackets, so it says I'm not including negative 2 and I'm not including negative 1. So those are rational functions. The next kind of function would be just a simple square root function. Square root of x plus 7. So with square roots, the limiting factor is that the argument, which is the thing inside the square root, has to be greater than 0, greater than or equal to 0. You know, if I let x equal 9, I substituted that in, f of 9 would be the square root of 9 plus 7, which is square root of 16, which is 4. So that exists, I have a number. But if I were to choose x equals 0, f of 0 would be the square root. Well, that would still work. 0 plus 7, get the square root of 7. But if x equals negative 11, say, I want to evaluate the function of negative 11, I'd get the square root of negative 11 plus 7, which would be the square root of negative 4. And there is no solution to that. You can't take the square root of a negative number with real numbers and get a real number. So what we have to say is what values of x would make it such that the argument, x plus 7, is greater than or equal to 0. So we set up this inequality, and then we solve for x. So we get x is greater than or equal to negative 7. And the way we would do that in interval notation is we'd have a square bracket, because it can equal negative 7, and we'd go all the way to positive infinity with a curved bracket. So that would, these are two ways to show it. Let's say f of x equals the square root of 3 minus x. So you use the same thought process. 3 minus x has to be greater than or equal to 0. So we subtract 3 from both sides. So anytime you add or subtract something, the inequality stays the same direction. So negative x has to be greater than or equal to negative 3. Now what we want to do is solve for x, not negative x. So if we multiply each side by a negative number, we get x and positive 3. But when we multiply by a negative number, we have to change the inequality. So instead of negative x being greater than or equal to negative 3, x is less than or equal to 3. So the way we do that in interval notation is this is less than 3. Think about number line. Here's 0, negative 1, negative 12. It's less than positive 3. So we would put a dot here, and then we would draw a line to the left. So the way we would do that in interval notation is negative infinity, comma, 3, square bracket. Because if x equals 3, I get 3 minus 3, which is 0. The square root is 0, 0. If I do number less than 3, 2, I get 3 minus 2, which is 1. Square root of 1 is 1. I have negative, if I have 0, I'd get 3 minus 0, which is 3. The square root of 3 is a number. If I did 4, I'd have 3 minus 4, which would be negative 1, so that wouldn't work. So you can see how that pans out. Now, if I have another term, like 7 minus the square root of x plus 2, all you have to worry about is the square root part. So again, I would say x has to be greater, x plus 2 has to be greater than or equal to 0. So x has to be greater than or equal to negative 2 for the domain. So we do this as square bracket, negative 2, comma, positive infinity, curved bracket. Okay, now what happens if we have a square root in the denominator. So let's say we have 5x divided by the square root of 3 minus x. So if you just have the square root by itself in the denominator, then you just have to make sure this argument is greater than 0, but it cannot equal 0. When it's in the numerator like this, it can be equal to 0, but the argument can be equal to 0 as well. It's being greater than 0. Here, what we have to have is that 3 minus x has to be greater than 0. Again, that's because this is in the denominator, and if this 3 minus x is equal to 0, you get something divided by 0, which is undefined. Okay, so again, what we do is we subtract 3 from both sides, multiply by -1, switch the direction of the inequality. And so again, you can see if I put in a number less than 3, 3 minus 2, say, that's the square root of a positive number, and it's not 0. So that works out. So again, how I would do this is I would, x is less than 3, so you'd have negative infinity on the left-hand side, positive 3 in the second term, and you'd have a curved bracket. So that shows that x is always less than 3, but not equal to 3. Now if the square root were in the numerator, so you have the square root of x plus 2 divided by x squared. So this denominator can take on any, well, it can't be 0, so that is a good point. So x cannot equal 0 based on the denominator. The numerator says that x plus 2 has to be greater than or equal to 0. So we have the equals part because it's in the numerator. So we subtract 2, get x has to be greater than or equal to -2. So what this is saying, it has to be greater than -2, but 0 is greater than -2, but it can't be 0 because that made the denominator go to 0. So how do we write that? So we'd say -2, comma, 0. Now it can't equal -2. So I'm going to put a square bracket, but it can't equal 0. And then that's in union with, again, it can't equal 0, and then all the way to positive infinity. So that's how you would represent that scenario. Let's do another one similar to that. Let's say f of x equals the square root of x minus 4 divided by x plus 2. So the denominator says that x cannot equal -2. It comes from x cannot equal, or x plus 2 cannot equal 0. So we're saying x plus 2 cannot equal 0, therefore x cannot equal -2. That's to keep the denominator non-zero. The numerator says that x minus 4 has to be greater than or equal to 0. So that says x has to be greater than or equal to 4. But you can see x is -2 is not in this interval. So this is all we have to worry about. As long as x is greater than 4, it's not going to be equal to -2. And so again, we would start at 4. Get a positive infinity, put a curved bracket there. And then the final scenario is if you had square roots in both the numerator and the denominator. So let's have x plus 4 over the square root of x plus 2. And we'll also do the opposite, which is f of x is the square root of x plus 2 divided by the square root of x plus 4. So in this case, the denominator, we say x plus 2 has to be greater than 0, because we can't let this, we have to have it positive, and you also can't have it 0. So that says x has to be greater than -2. In the numerator, we have that x plus 4 has to be greater than or equal to 0. This is in the numerator, so it can be 0. So we get x is greater than or equal to -4. So looking at these two, if x is greater than -2, then it can't equal -4. So this one supersedes that one. So you'd have -2 comma positive infinity for that interval. Now over here, you've got the denominator, x plus 4 has to be greater than 0, and or x has to be greater than -4. And the second part is x plus 2 has to be greater than or equal to 0, because that's in the numerator. So you get x is greater than or equal to -2. So this one is -4, which isn't in this interval. So we take this one's the one that applies. This one doesn't count, because if you had x equal to -4, or actually between -4 and -2, it's still going to be less than this value. So we would have x, in this case, is greater than or equal to -2. Okay, so that's kind of how these things work.